mentioned about problem methods for logic specification. So you have, let's say, a motion planning problem and there is uncertainty in the environment or the robot itself. And you eventually want it to reach a goal. So for example, the slippery robot here. Now, my specification is that I want a behavior, but the robot should be able to say that I cannot do it if it is not able to do it. So where does that come into play? Because in the example that you showed, there's a narrow passage, and if the slippery is too high, then it should say that, oops, I can't do it. So where does that come in?
In the case that I would show, it would try to compute a backwards reachable set from the target zone. And, you know, we approximate things so we can do the computations fast. But if the approximation tells us it's not possible, we either try to get a better model or we say it's not possible. So it actually won't give a solution to, it won't show you the set that contains your initial condition and your target set.
But you would know that if
Right. I mean, that's often the most interesting question to ask of these systems. In my case, I'm often looking at ecological problems where we want to say, you know, prevent this species from going extinct, and while you're doing that, also, you know, maximize economic value. And there may be no solution, and learning that fact is extremely important to know. So it's also sometimes quite difficult to compute.
Yeah, in the work I was doing, it actually computes a probability of satisfying the specification, and so it can come back and say, I can do it. The behavior that I'm going to execute is going to satisfy it with 2% probability, but you know that's the best I got.
Carnegie Mellon University. This question is for Claire and Tom. You both spoke about systems that provide safe operation by becoming aware of how accurate or inaccurate their learned models of themselves may be. Do you think that self-awareness is a prerequisite to safe operation?
Self-awareness is a bit of a loaded term.
I don't think it's a prerequisite, but I think if we're talking about systems that are flexible, that are adaptive, then I think this is my intuition from working in this. I think it definitely provides, it enables this solution, this, you know, the ability to understand limits and understand, you know, when you have to ask for help, when you have to ask a human operator for help. So I wouldn't call it a prerequisite because I think you can do it without it.
Right, but the alternative to self-awareness, let's rephrase that as that the system has some continuous monitoring of its own behavior, and it's trying to detect failures in its model in various ways, right? Anomalies, unexplained variation, you know, exceeding bounds that it thought would never be exceeded in Claire's case. If we can prove before deployment that those will all be satisfied, then we don't need to do continuing monitoring. But in most of the cases here, we cannot prove that in advance, particularly if the system itself is learning at runtime and we don't have full control of the experiences it's going to have. How do we know how it will evolve? We have the Microsoft Tay as a sort of toy counterexample. And so I think we do need self-monitoring. And you know, my own personal hypothesis is that's what one of the roles of consciousness in humans is, that it is this continuous self-monitoring. But I'm sure the scientists who study consciousness think it does a lot more than that.
A question from personal experience. Emily mentioned the medical field several times. What happens if you have multiple doctors involved, each doctor makes the correct decision at that moment for the patient, but in the end result, the system fails and the patient dies, all based on what was perceived to be correct data? How does any of the models account for something like that? I mean, all the input data was correct, but the outcome was still wrong.
So I think that's a great issue, and I think that speaks to the fact that these are very, very complex systems. And so in those cases, I think I would argue that those individual decisions were correct given perhaps the available information, but there was clearly missing information or missing or model misspecification, maybe in a doctor's mind. for why things evolved, or it was a highly stochastic system, right? So there's the question of could it have been avoided, which is one issue, or the other is was it wrong decision because we don't have enough information? And I think that just like this happens in real medical practice right now with humans, it'll be an equal issue of how do we have systems that can collaborate and coordinate across the many different streams of information they have in order to try to avoid those sort of situations.
Hi, I was wondering, ensemble methods have been mentioned a number of times, they're very widespread as a way of boosting or backing whatever, but increasing the aggregate reliability of your report. And by analogy, in the safety critical software community, N-version programming was used for a long time, had demonstrable improvements in the robustness. But then some pretty rigorous analysis showed that the performance envelope from N-version programming wasn't nearly as well understood or useful as you might think. And so it's subject to common mode failures in ways that were not predictable, et cetera. And so N-version programming is still used at times, but with big caution bars around it in safety critical systems, and the amount of credit you get in terms of increasing safety for using N-version programming is sort of difficult. So I'm just wondering if there's similar analysis in the machine learning community about how much we can really say about how much of an improvement in the aggregate reliability we get from ensemble.
No, I think. I mean, I'm really eager to learn more about this experience with N-version programming because, I mean, one thing we have maybe a little bit more control over in the machine learning case is that we actually, all of the different versions are usually constructed by some systematic manipulation of the input data, right? Or we could also imagine in the robust case, you could have a bunch of versions that were prepared with different levels of robustness, and you can then monitor and see when things are going wrong. But yeah, I don't know that we analyze our ensemble work primarily in the framework of bias and variance, and those are fairly well understood from a statistical point of view. And common mode failure, I guess, because each model is trained on, let's say, 62% of the data. 62% of the models all might be influenced by one very bad outlier, and so I guess that's a common mode failure that the majority could be wrong because of one data point. But in robust statistics, you would try to detect and remove the influence of such a highly influential data point.
Empirically,
So-
these ensemble. Yeah, I'm sorry. Go ahead.
I was just going to say, the inversion programming, there was a well-known study from Nancy Levison at MIT, and the common mode, I think, is more common, in that they started all with the same specification, and that kind of over-determines the implementation. So I think that, but I think it would be interesting to speculate here on what's common and what might be the pitfalls.
Right. Well, the training data is common, and maybe the loss function. So we should think about that because we do clearly see, like one example of this is these adversarial data points for deep networks. Right. People have found that if you train a deep network on a data set, you can cleverly design data points that will make the system very confident and very wrong. And what's interesting is that if you take those same examples and go over to a different learning algorithm but train on the same data, it will be also a very confident and very wrong in that other thing. So even though we're using very different learning algorithms or very different architectures, the common mode is the same data or very similar data sets.
But that's not the only way that ensembles are used in this kind of AI setting, right? So sometimes, for example, the Watson question answering system that played Jeopardy, they had different subsystems that were developed somewhat independently that really were intended to attack slightly different problems, and then they were all run in parallel to see which ones were going to be able to contribute to a given answer. That seems to make a big positive difference if they're actually developed well in terms of the coverage that they can produce. So there's some modes that I think are empirically been shown to be very, very useful for having these separate answers blended together.
But I think most of this has been done in the context of prediction only. And so I think when we start to think about algorithms that are making decisions and changing the distribution of data they get, it's much less well understood, even in the ensemble case.
We could take a couple more questions.
Go back to the medical context real quick. How do you guarantee that whenever you design a classifier over medical data, notoriously unique, that has a 99% accuracy, you're not going to always kill the same 1% of the population.
So I think that's a really important issue, and we were just talking earlier today about a New York Times article that came out this weekend talking about discrimination in algorithms, and I think this is an incredibly important issue. A number of people are working on this. Personally, some of the work that Anupam Datta is going to talk about this afternoon, I think we'll cover this. And in my own lab, we're thinking about what we joke as well-behaved agents, so in order to make guarantees that for none of the groups that could be covered by the data set will we be systematically having worse performance.
Reinforcement learning. I study very young children in these types of contexts, and one of the things that I look specifically at is their transition between what I refer to as natural response and guided response. Basically, what's your motivation to, okay, I'm observing something, and now I'm going to try it myself, and the difference between, being willing to listen to a coach. So so this is a good first step, but these things get really complicated fast. So I don't know if you want to speak to that. So that difference between, okay, I've watched something and I've created my model, but what might be wrong about it, and where I go to, do I look at the data, do I reorganize?
Yeah, I mean, so far the majority of inverse reinforcement learning work in the AI community has been in terms of what's called apprenticeship learning. So I'm just going to show you stuff, and then you should do it. One of the things that we're finding, I mean, it's definitely much more subtle than that. I agree with you. One of the things that we're finding is that, in fact, if you have the standard way of doing inverse reinforcement learning is you have an expert demonstrate, which is to say, just do what it does to optimize. What we're finding is that a teacher, somebody who actually is doing the good thing, but in a way that's more cognizant of the fact that the system's going to try to learn from it, that they can actually tweak their performance in a way that actually makes it easier to learn the right thing. And so there's all sorts of levels of subtlety about how the right way to do that ought to be. I think bringing the notion of teaching into machine learning is actually really critical, because I think that often it's the case that the way that these systems are going to learn about what's important to us is they have to interact with us. They have to be raised by us.
Very quick final question.
We often approach safety as training for optimized performance, but in some cases it seems like building in safety to the way the system learns actually turns out to improve performance. For example, as I understood it, Claire mentioned that with the quad rotor vertical control, it was improved actually by having a safety region model. So even if safety trades off against performance, it's still important. But to what extent do you think that safety mechanisms can actually improve or enable performance as opposed to hinder it?
In most of the systems that, in fact, I'm trying to struggle to think of a system where this doesn't, they've always been butting heads at each other. Even in that example I showed, as soon as you make the trajectory, the performance trajectory violate the envelope a little bit, it's going to try to get out of the envelope and be pushed back. And that causes an issue because you have to blend, then you have to really think about how you're blending these two functions together. But it's an interesting question. And I think that, where they're tied together closely and where there's a sort of synergistic effect between the safety value function and the performance value function is really in a system where you actually define high performance as that's also correlated strongly with your safety function. So we talked about education and all sorts of, I deal a lot with moving vehicles, but in financial systems or education systems and healthcare systems, I think there we see much stronger correlation between them.
Let's thank our panel.